Ever wondered how AI models like GPT or BERT achieve such remarkable language understanding? The answer lies in a revolutionary architecture that's reshaped machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, exploring their self-attention mechanisms, positional encoding, and why they've become the backbone of modern NLP. Buckle up, this is the inside story of one of AI's most powerful innovations. Before transformers, recurrent neural networks (RNNs) and convolutional neural networks (CNNs) dominated sequence modeling. But they had a critical flaw. They struggled with long-range dependencies. RNNs suffered from vanishing gradients, while CNNs relied on fixed receptive fields. Imagine trying to understand a 1,000-word S. RNNs would forget the beginning by the time they reached the end, and CNNs would miss context beyond their filter size. This bottleneck demanded a new approach. Enter the transformer, introduced in 2017 by Vaswani et al. Inattention is all you need. The key innovation: replacing recurrence and convolutions with self-attention mechanisms. Instead of processing sequences step by step, transformers analyze all elements simultaneously, weighing their relationships. Think of it as a neural network that can look ahead and look back at every word in a sentence, dynamically adjusting focus based on relevance. Let's break down self-attention. For each word in a sequence, the model generates 3 vectors: queries, keys, and values. The query for a word asks, "What am I looking for?" The key for another word answers, "What do I represent?" The dot product of a query and key determines similarity, which is then scaled and passed through a softmax to produce attention weights. These weights are multiplied by the corresponding values, aggregating information from the most relevant words. This allows the model to capture complex dependencies, like resolving pronouns or understanding context. But wait, how does the model know the order of words? Unlike RNNs, transformers lack inherent sequence awareness. The solution: positional encoding. This is a learned representation added to word embeddings, encoding each word's position using sine and cosine functions of different frequencies. The result: a continuous, scalable way to inject sequence information, enabling the model to distinguish between cat sat on the mat and mat on the sat cat. To enhance representational power, transformers use multi-head attention. Instead of a single attention mechanism, the model splits queries, keys, and values into multiple heads, each capturing different aspects of the data. For example, one head might focus on syntactic relationships, while another detects semantic patterns. These outputs are concatenated and linearly transformed. This is followed by a feed-forward network, a simple MLP, that further processes the information. This encoder-decoder structure allows the model to both understand and generate text. One of transformers' greatest strengths is scalability. By parallelizing computation across all sequence positions, they outperform RNNs in training speed. However, the quadratic complexity of self-attention, (O(n)2) in sequence length, pose challenges for long sequences. Recent advancements like sparse transformers, longformer, and linformer address this by optimizing attention patterns, making it feasible to process documents thousands of words long. Today, transformers power everything from chatbots to code generation. But they're not without challenges. Their massive parameter counts demand immense computational resources, and their black box nature complicates interpretability. Researchers are tackling these issues through techniques like knowledge distillation, efficient attention variance, and explainability frameworks. The future: more efficient, interpretable, and generalizable models that bridge the gap between human-like understanding and machine precision. Transformers have redefined what's possible in AI, but their journey is far from over. As we push the boundaries of scale, efficiency, and understanding, one thing is clear: the self-attention mechanism is a cornerstone of the next era of machine learning. If you're curious about the latest breakthroughs, stay tuned. Next time, we'll explore how researchers are making transformers more efficient for real-world applications. Thanks for watching, and remember, the future of AI isn't just about bigger models, it's about smarter ones.